Yes, already. I'll do that.
Okay. So, ẹni wá share méjì pẹ̀lú àwọn ọmọ yẹn.
Ben, I'll do that.
Aha. Ẹ ṣé gan ni. Mi ò mọ tó ṣe YouTube. Only I'm not enabled to live stream with my Zoom. Àbí
You're online
CITs
now,
ló máa enable wa ni.
You're online now.
Yes. Okay. Ẹ ṣé gan sir. Hello? So, good afternoon, students. Good afternoon, everyone. Today is going to be a continuation of where we stopped during the last class. So today is going to be a continuation of where we stopped during the last class. In the last class on Tuesday, we were able to discuss about the Newton's laws of motion. And under the Newton's laws of motion, we were able to actually treat that we have three Newton's laws of motion. Three laws were proposed by Isaac Newton. And the first law states that an object will continue to remain in a state of rest or move with uniform velocity unless a force acts on it. That is the first law of Newton. The second law states that the force applied in order to move the object from a state of rest or maybe to change its velocity, that force is directly proportional to the acceleration that will be obtained after applying the force. While the third law states that for every action there must be an equal and opposite reaction. There must be an equal and opposite reaction. That means when you apply a force, you must get a reaction. For example, if I decide to sit on a chair, or if I jump from the top of a table to the ground, after jumping to the ground, I've exerted some form of force on the ground. Definitely the force I have exerted on the ground, I must experience an equal and opposite force. And that is what we refer to as a recoil. Even a military man or an army shooting a gun. And that's why they have to position themselves in a way that they will not actually fall down. So that's basically what happens with the 3 Newton's law. So we're able to solve some simple example. If there's time today, I might likely treat 1 or 2 more on that, our first, on what we had last week. Now, today, we'll be moving on to linear momentum. We'll be moving on to linear momentum. And when we talk about linear, that means it is moving in one direction. When we talk about the Cartesian coordinate, basically when we discuss about the Cartesian coordinate, basically you all know that we have our y, our x, and our z. So if an object moves in any of these directions, that is what we refer to as a linear. That is what we refer to as linear. So when we now discuss about momentum, momentum is as a result of the movement of the object with respect to what kind of force is exerted on that kind of object. We would then say it has gathered some momentum. That means it has the potential of moving. But if it moves in one direction, or in a straight line, we say it has linear momentum. Now, what we are to discuss today, we will discuss about momentum and its relation to force. We'll also discuss about the conservation of momentum. Likewise, we'll also discuss about collisions and impulse. We will discuss about collisions and impulse. Thereafter, we'll discuss about the conservation of energy and momentum with respect to collisions. Also, we discuss about elastic collisions in one dimension. Then we discuss about the inelastic collision. We will discuss about inelastic collision. Later on, we will discuss about collisions in 2 or 3 dimensions. Then we'll discuss about the center of mass. Likewise, we will discuss about the center of mass with respect to human body, the center of mass and translational motion. Now, let us begin with today's lecture. Momentum and its relation to force. I had said that when you have an object, the moment you apply a force to an object, let's assume we have a football player now. This ball, the initial velocity is 0 meters per second. The moment the football player applies a force, definitely it will change velocity. When it changes velocity as a result of the force applied, it will start to move. That means it has gathered some momentum. Therefore, momentum is defined or represented symbolically as the product of mass and the velocity. Momentum is defined as the product of mass and velocity. Product of mass and velocity. So it is only when we say our momentum is usually represented as P, and you can see it's a vector quantity. Momentum is a vector quantity. That's why you have the arrow above it. Likewise, the velocity is also a vector quantity. So momentum is defined as the product of mass and velocity. So when you have that, it is only when you have change in momentum. For example, if I have change in momentum, which is the delta P, that means I'll have the mass, because the mass of the object will not change. Then I will now have the change in what? Our change in velocity. That is when I will then have the mass, then I will then have my V, final velocity, minus what? The initial velocity. That is the representation of what we refer to as change in velocity. That is change in velocity. So now, but when it now comes to the rate of change of momentum, this is the change in momentum. So the change in momentum that you add here, delta P, is a result of the initial final momentum minus initial momentum. That gives us that. That gives us the change. But when we now discuss about the rate of change of momentum, when you say something as a rate, rate refers to, that means it is changing with respect to what? Changing with respect to time. That means it is changing with respect to time. So that means we now want to have that. So the rate of change of momentum is, we can write that as a result of this, the force, summation of the total force applied, then that will now be the change in momentum divided by what? With respect to the time. So when we have this now, we can then rewrite this as what? The change in momentum, what we have here, that will be the mass. Then we have our final velocity minus initial velocity divided by what? The time. Such that at the end of the day, we can have that force multiplied by the time. That's the change in time. Then which then gives what? The mass V minus U. So we can then say your Ft, which we'll still see later, the product of the force applied and the time, will refer to this as impulse, which will now be equal to what? Change in momentum. Change in momentum. So that is what we have. So from here. So when we discuss about rate, rate means it is changing with respect to time. As the momentum is changing, the time is as well, it is as well changing. That is why we now have here rate of change of momentum. So that rate is the changing with respect to time. And the change in momentum is this. So the rate is what you have here, while the change in momentum is just this. So that is what we have there. So this can be shown using the Newton's second law. And how can we show that using the Newton's second law? Is just what I have explained here. The Newton's second law So the Newton's second law, what we studied on Monday, state that the force is equal to what? MA. But from here, Our F is equal to what? M. Then acceleration is change in velocity with respect to what? With respect to time. So from there, you can observe that we can then get our rate of change of momentum. So the rate of change of momentum is derived from the Newton's second law. That's what we have. Now, when we discuss about momentum itself, for example now, because when an object gathers momentum, just like we have in object A here and that of B, we have object A and we have object B. If object A gathers momentum in the direction of B and B gathers momentum in the direction of A, both of them are bound to collide. There's collision here. There's collision here. So when they collide, the collision can either be an elastic collision or it could be what? An inelastic collision. Those are the two forms of collisions that we have. When the object A and the object B, when they collide, they can exhibit either of the collisions based on the constituent of their atoms. Now, the collision that we can observe can either be elastic or what? It could be an inelastic collision. So when we talk about elastic collision is a situation where the objects collide and they move apart separately. The objects will collide and they move apart separately. But when the objects collide and they stick together, that is when we have an inelastic collision. They stick together and move towards one direction. That is what we refer to as inelastic collision. But when they collide and they move separately apart, that is what we refer to as elastic collision. And that's what we can observe here. Now, when in the process of collision, either elastic or inelastic, momentum is always conserved. Momentum is always conserved in any collision, while the energy might not, based on the type of collision. Based on type of collision. So what I mean by this is this. For elastic collision, and energy are conserved. Why for inelastic collision, momentum is conserved while the energy not conserved. So those are the two things. So when we now talk about the conservation of momentum, this is what we now have here. When we discuss about conservation of momentum, we now have a situation where momentum before collision is equal to momentum after collision. That is the law. Momentum is always conserved for any form of collision. Momentum is always conserved for any form of collision. But the energy, it depends on the kind of collision. If it is an elastic collision, the momentum is conserved. While for inelastic collision, the momentum is not conserved. It is not conserved. So that is what we have when it comes to collision. But take note, for any form of collision, momentum before collision is always equal to momentum after collision. And that is what you have here. This is the momentum of body A added to the momentum of body B. That is the total momentum before collision of the two bodies. While after collision, momentum of A, body A added to momentum of body B. That is what you have there. So this formula still holds for what? For elastic collision. Why, as we progress, we'll see that of the inelastic. So in this situation, for momentum to be conserved, that means you must not apply any external force. For momentum to be conserved, there must be no application of any external force. Because once you apply that, that means your F will then be equal to ma. Second Newton's law comes to play a role. So for momentum to be conserved, and the direction might be changed, velocity might be changed, that is the reason why there must be no external force. External force applied is 0. Now, conservation of momentum, still on that. More formally, the law of conservation of momentum states that the total momentum of an isolated system. Why did we put isolated? Isolated implies there is no external force. External force is equal to what? 0. That's why it's an isolated system. It has no interaction with its environment. So the net force on it is 0. So the total momentum of an isolated system of objects remains constant. It remains constant. Like when you look at this now, you have coach A, that's the train coach A, you have train coach B. But you will observe that the train coach B is at rest. Why this is moving with a velocity of what? 24 meters per second. That is before collision. But after collision, both of them now collide. But you now observe that after collision, both of them now move in the direction of what? The direction of X direction. It moves in the X direction. So if this occurs now, we were now asked to find the final velocity of both of them. Because you can now see that they have now stuck together. They are stuck together. So this kind of collision, when they stick together, is what we refer to as an inelastic collision. So for an inelastic collision now, they will then have a common final velocity. They will have a common final velocity. If you look at what we have here now, please hold on. So now, if you look at what is here now, we have this. This is the formula for conservation of momentum. But here, when they now stick together, like we have here, so using the law of conservation of momentum, that means we will have the mass of A, the initial velocity of A, added to the mass of B, initial velocity of B. Then after collision, we now have the mass of A, this of this, plus the mass of B, then the final velocity of B. But because B was initially at rest, so if we put 0 here, this goes off. So we are left with what? The mass of A with this, which will now be mass of A, final velocity of this, mass of B, then we have this. So were it to be an inelastic collision where they collide and they move separately apart, this formula holds. There will be no common velocity. But here, they stop together, there's a common velocity, and they move in the same direction. That means for inelastic collision, VA must be equal to VB, and that will be equal to a common V, which is this. So we can then have that our MA, UA will then be equal to V, then we have MA plus what? MB. So it's quite easier. So once we know the mass of A and the mass of B, because we add the initial velocity of A, then we can calculate this common velocity. This is for elastic. But for inelastic, because they will move together, the final velocity of A will be equal to final velocity of B, and they will have a common velocity. And that is what we will have there. And that gives us this. So that is the way to solve the problem. That is the way to solve that kind of problem. So I hope with the little explanation I have given, you now understand what momentum is, the product of mass and velocity. When we talk about the rate of change of momentum, that's the momentum, change in momentum divided by change in time. Then when we now talk about conservation of momentum, that means we'll then have total momentum before collision will be equal to total momentum after collision. That is the law of conservation of momentum. But however, and it's given by this formula, I said earlier, for this kind of collision, if you have elastic collision, you have energy, the momentum and the energy are conserved. Why for inelastic collision? For inelastic collision, you will have this conserved, the momentum, while the energy not conserved. So that is what you have there. So based on that, and I've said if it were to be elastic, they collide and they move separately apart. But for inelastic collision, they collide and move together with the common velocity. And that's what I have solved here based on the problem we have on this slide. That is what we have here from year to year. Now, the next slide, still discussing about conservation of momentum. Momentum conservation works for a rocket as long as we consider the rocket and its fuel. Initially, the rocket was at rest here. Here it was at rest. And that is why your P, which is equal to this, if this is 0, that means your momentum will be 0. Is it at rest? Yeah. But the moment you launch it, the moment you launch this, it releases some gas, that is fuel being wasted, and the rocket moves in the other direction. So the mass of gas and the mass of rockets together, because initially the gas was inside this, it constituted part of the mass. So once you start releasing it, you cannot jettison it. So there's still law of conservation of momentum. So the mass of gas with its velocity mass of gas and the mass of the rocket with the velocity. It will now give us the total momentum of the whole entire system. Now, just like I said, we said that the rate of change of momentum is determined from the second Newton's law. So from here, we have V divided by T. So from here, you can then say your Ft will be equal to the change in momentum, whereby we refer to this as the impulse, and this as change in momentum. Now, if you remember from your O levels, I said then you will be asked to actually define impulse. And you see quite a lot of wrong definitions, even from some revered textbooks. So what is impulse? Impulse itself, if you're asked to define impulse, impulse is the product of large force and short time or duration. For example, if you slap somebody, pa, or you have a carpenter trying to hit nail into the wood, pa, 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 you can see there's a large force, but the hammer is acting on the nail within a very short time. The time of interaction is very short. That is what is defined as impulse. It is not just product of force and time, no. It's a product of large force acting within a short time. Product of force and a small duration. So that is what impulse is. So depending on the question given to you, you can determine what you can do with all this. So the force multiplied by the change in time. And that is what we have here. So that is an impulse. But mind you, this is large force and a short time. Now, the next slide, where we talk about collisions and impulse. For example, if there happens to be an accident, maybe of two bikes or two cars, when they collide, you know, they collide with a large force. If they are moving in opposite direction with a high speed and they collide, the collision is sudden. So when they collide, you observe, you can see the force is very large. You can see it is to the maximum. But the time of action is very short. You can see it is in milliseconds. The time is in milliseconds. So the kind of collision and impulse, so there is a relationship between collisions and the impulse. The impulse tells us that we can get the same change in momentum with the large force acting for a short time, you can see. Large force acting for a short time, or a small force acting for a longer time. You can see it's vice versa. Or a small force acting for a very short, a longer time. So this is why we should bend your, this is why you should bend your knees when you land. For example, if you are jumping from a fence into a compound, when you are landing, you don't just stand straight. You need to bend your knees because there will be an impulsive force on your knees. And if care is not taken, you might end up damaging your knees. So when you are landing, you bend your knees as if you are squatting. So you land like squatting. So it's the same principle you see the airbags. Modern day cars now have airbags such that there's a sensor in front of the bumper. If there's an head-on collision of the car, the airbags deploy themselves immediately. Poof, poof. They come out like pillows. So the airbags of the car, they are surely deployed to protect the driver and the passengers. So while landing on a pillow hurts less than landing on a concrete. So it's just like the airbag issue. When there's a collision, the airbags of the car, they deploy. So if you are landing directly on the ground from a specific height and you are landing on a pillow, there's a difference. There's a difference between the two. So when landing on a pillow or a mattress, you might not even need to, because there's something that is cushioning the effect, the impulse that might be felt by your knees. Now, conservation of energy and momentum. I had stated all this earlier, that if you have here you have two objects, A and B, moving in opposite direction. A is moving with the speed of VA, while B is moving with the speed of VB. If both collide, you can see this is the collision stage. There was a collision, but they move separately together. That's why it's called what? Elastic. But inelastic, if they collide and they stick together, or if they collide, even if they don't stick together, the distance of separation is not too large. The distance of separation is not too large. That is what you have. The distance of separation is not too large as well. Either they stick together or the distance of separation is not large. But for elastic collision, they move separately apart. Here we have two objects colliding elastically. We know the masses and the initial speed. So since both momentum and kinetic energy are conserved, we can write two equations. This allows us to solve the two unknown final speed. The two unknown final speed. Now in this situation, you can see they are moving in the same direction, but they collide. After collision, they move separately apart. So in this situation, the momentum and the kinetic energy both are conserved. I said that earlier. I mentioned that earlier. This is the initial stage, and this is the final. So they collide and move apart. So in this situation, we are writing the equation now. It will then be MA plus VA. That will be MB, VB, which will be equal to MAVA, then plus MBVB. So that's the law of conservation of momentum. And that's what we have here. So you can determine the speeds depending on what you are given in the question. Now for inelastic collision, this is the initial. And this is the final after collision. With inelastic collision, some of the initial kinetic energy is lost to thermal or potential energy. So it may also be gained during explosion, as there is the addition of chemical and nuclear. A complete inelastic one is one where the objects stick together afterwards. So there is only one final velocity, just like this. You can see that the bullets stuck into this and they move together. Now, instead of having one mass now, it will now be the mass of the bullet and mass of this. And that is what you have been represented here. So if it's inelastic now, here your Vm is 0. Here you have M multiplied by your V. So that's V here. Then plus capital M multiplied by Vm. Then which will then be equal to what do you have there? It will have a common velocity. Then you have M plus what? M plus M. But because this was at rest, so if 0 is here, this goes off. So you are left with this. So you can then find, if you are given the mass, the masses and the final velocity, you can then calculate this common final velocity. You have the initial and you have this. So that is what you have. Now collision in 3 dimensions, just like this. If it collides here, so you can describe the position of the object in 3 dimensions. That is along the X, along the Y, along the Z. If it is 2 dimensions, that means along XY, XY. With 3, that will be along XY, Z. So problem solving is not it's nothing too serious. Now, what do we call center of mass? We've been used to center of gravity right from our O levels. We'll now see, so we have what is called center of gravity. You might have that represented as CG. Then we also have center of mass. That's represented as CM. So if you look at these divers now, in order for us to be able to locate the center of mass, in A, the diver's motion, you can see a diver diving into a swimming pool. The diver's motion is pure translation. When you say it's pure translation, that means it's in a straight line. B, it is translation plus rotation. You can see it just jumped and it's in the Y direction, jumped and it moved and still went into the pool. But here you can see it jumped and you see it rotating. Continues to rotate, that is, it started the motion this way until it dived into the water. That's why we said this is both translation and rotation. Why for this? It is just translation alone. So this point is called the center of mass. There is one point that moves in the same path. And what is that one point? That is the body mass of the human being that moves in the same path. A particle will take if subjected to the same force. So even if you have a ball or a particle and you subject it to the same force, you find out it takes that projectile motion. So that's why this point is called the center of mass. So that trajectory that is going to take, that is what we refer to as the center of mass. Now we have another illustration. The general motion of an object can be considered as the sum of the translational motion of the center of mass plus rotational plus vibrational and other things. You can see these spanners. Some are vibrating, some in translational motion, some are also rotating. So you will observe that the kind of movement you observe here are 3. So they are all doing all this about their center of mass. They are doing all this about their center of mass. That is what we have there. So when you discuss about the center of mass, if you have various objects, you have body A, body B, they are at a specific distance from the center of mass. So the center of mass is here. So the difference between the center of mass and the center of gravity is at the point where the acceleration due to gravity of the earth pull is acting on that object. That is what is called the center of gravity. The point at which the earth's gravitational pull is acting on that particular object. While the center of mass is the point about which the atoms of the object are performing certain form of motion. It could be translational, it could be rotational, it could be vibrational. So that is what you have there. Now, the center of gravity is the point where the gravitational force can be considered to act, just like I have said that. So the pivot is here where it is suspended. Then you can then see this is where it is suspended. Then the center of gravity, the earth gravitational is acting here. So which will be a product of the mass and the acceleration due to gravity. So center of mass is the same thing. We can see difference between center of mass and center of gravity. For a donut, center of mass is in the center of the hole. This is a donut. The center of mass is here. So it's about this point that the donut will perform different motions, either rotational, translational, or whatever. But the center of gravity, that is the point where you have your G acting. The G acts there downwards. So those are the differences. So the location of the center of mass of the leg circled will depend on the position of the leg. You can see when the leg is bent, this is the center of mass. When it is bent, this is the center of mass. But when it is straightened, you can see the center of mass has changed. So depending on the position of the object, that determines the center of mass. So high jumpers have developed a technique where their center of mass actually passes under the bar. So jumping, doing some sports are physics related. So if a jumper is able to achieve or develop a technique where his center of mass is going to go under the bar, so it's going to be easier for that kind of jumper to always go over the pole or higher bar. As they raise it, if he could also raise the center of mass, then it will always go over the bar. So the sum of all forces acting on a system is equal to the total mass of the system multiplied by the acceleration of the center of mass. So that is what you have. So the sum of all forces on an object, if you have an object and several forces, so the sum of the forces is a product of the mass of the object and the acceleration of the center of mass. Because as it performs the motion, the center of mass also is responding. So these are the different parts that you can see the center of mass being exhibited. So these are the stuffs we have learned so far. And we will observe that the momentum, we have been able to study that it is a product of mass and the velocity. It is a product of mass and the velocity. And we said from the Newton's second law, we can determine that the ratio of the change in momentum to that of the time gives us the net force on an object. So total momentum of an isolated system. The total momentum of an isolated system is conserved. Just like I mentioned earlier, total momentum is conserved because for an isolated system, there's no external force acting on it, it's zero. So during a collision, the colliding object can be considered to be an isolated system, even if external force acts, as long as they are not too large. So momentum will therefore be conserved during any collision. During any collision, momentum is conserved, but while the energy varies. For elastic collision, momentum is conserved, while for inelastic collision, the momentum is conserved, but energy is not conserved for inelastic collision. But for elastic, both the momentum and the energy are usually conserved. Here we've been able to see that this is what we refer to as impulse. And we have said impulse is either a product of large force and short time, or you can have small force acting within a large time. So either of the two. So in an elastic, total kinetic energy is conserved. In elastic, some kinetic energy is lost. In a completely inelastic, the two objects stick together and move after collision. That's when they have a common velocity. So the center of mass of a system is the point at which the external force can be considered to act. Center of mass, point where external force. Y for center of gravity, point at which the Earth's gravitational force act. That is what we have there. So I think with what I have just explained, that is all about the linear momentum. That is all about the linear momentum. Now, sequel to what we treated on Monday, I was discussing about an elevator. And what you have here, you have exhibition of the different laws of Newton. Here you have a scale. Scale used to measure the mass. And this is the elevator. In this situation now, if the elevator is moving down, that's why it is accelerating. You have your A. But the mass of this human being is M. So if you want to determine the weight, you multiply by your G. So if it's exerting a force, which is mg, on the scale, based on Newton's third law, there's an equal and opposite what? Reaction, which is our Fn. Now, when this happens, you need to be able to determine the total force of the human being with respect to the second law. That will be total force is equal to ma. However, in order to get the total force, it will be a result of the weight and the reaction. So you need to subtract the two. And why do you subtract the two? The two, because you see that they are in opposite direction. So you need to subtract the normal reaction from the weight, which will still give us ma. But A from the question is what? 0.2 G. And that's why you have this. So from here, if you collect the like terms, your Fn will then be equal to mg minus this. So you have this. So if the mass is put under 0 degree gravity, we can get the reaction of the scale on the human being. The reaction of the scale on the human being. Now, the normal force is the force the scale exerts on the person and is equal and opposite to the force she exerts on the scale. Now, you can then have a downward force, which is 0.8 this. So this can be sorted out. So our weight is what? Is still mg. The weight is mg, mass multiplied by 9.8. Then you then multiply by 0.98 for us to have the weight of the lady on the scale inside the elevator, which is then given as 640. But the scale needing to exert a force of this. The scale will need to exert a force of this. So if we solve for the 0.88, we have 52 kilograms. You can see there's a reduction from 65 to 52. And why is this so? Because as it continues, as it accelerates downwards, the weight of the lady reduces. But were it to be that it was accelerating upwards, it's going to increase. It will surely increase. But take note of that. But if the elevator is standstill and no force acts on it, that means you will have what? You will have a situation where if the acceleration is 0, that means it's not accelerating. By Newton's second law, if it's not accelerating, this will be 0. So you have your normal reaction is equal to mg. The normal reaction is equal to mg. So the scale will read this. If it's not accelerating, the scale reads 65. But the moment it starts accelerating downwards, the human being feels lighter. Feels lighter. And all this as a result of what we study in physics, which is called relativity. Motion of one object to the other. So when it's accelerating downwards, there is loss of mass. There's always loss of mass. But when it's moving up, there's always an addition. There's always an addition of mass. But when it's uniform velocity, or your u is 0, once your u is 0, then the scale reads what it should read. When it starts to move, it changes as a result of relativity. Changes as a result of relativity. So I hope with the little I have explained, it should be clearer that what we have taught this week, we have discussed about the Newton's laws, and we have discussed about linear momentum. So basically, those are the things that we have been able to treat this week. So thanks for the audience. I wish to see you next time my group takes over. Another group will take over next week, and they will be teaching you next week. So I wish you a wonderful weekend ahead, and hope to see you next time. Thank you.